Okay, so we've started meeting with groups, lab groups, and the lab reports aren't, I think I exaggerated, they're not that bad, okay? I just got kind of carried away on that. But so it only takes like 10 minutes. So we've already taken care of 2 groups. I've got appointments for some other ones. Has every group made an appointment? Or maybe there's one group that hasn't. Has every group made an appointment? Is that right? Okay, all right. Good. So the first thing we want to do here is, you remember this thread, it broke, the connection broke here yesterday. So, and it's probably a good thing because I didn't really make a connection between this. This is the problem that we solved, right? We've got a normal force here that causes this mass to go to, it's going to go through this loop here. If it has sufficient energy, it's going to do this loop here, right? If it doesn't, it goes into projectile motion here till it bangs into over there. So we have an apparatus, I showed you yesterday, that does this, but it's complicated because it uses a rolling ball, not a sliding ball. So how can we experimentally confirm this? Well, this is the easy way to do it. Now we've made a leap going from here to here. Okay, one leap is, I've flipped this, unfortunately. So here you're going to the right and you do the loop. Here, it's going to your left. Sorry. It's okay for me back here. But that's not a problem, right? That shouldn't be a problem. But where's the normal force here? There is no normal force. But what is there? A tension force. And that plays the role of the normal force. So this is how physicists think, right? We try to look at the big picture. I want to confirm this. I'm not going to start thinking about ramps that, No, I'm going to do this. This is much easier. We remove the problem of the rotational kinetic energy too, right? No rotational kinetic energy here. Okay, so we predicted, the theory predicts that for it just to go around the loop, you want to go half of a radius above it here. So that's where the black tape is. And if we go more than that, it should have no problem. And you see it goes around fine, right? It executes the loop. If we're well under it, boom, goes into projectile motion, doesn't make it. And the critical case is predicted to be right here with at this level of the black tape there, right about there. And it's hard to see, but it looks like it executed it, right? It went through the loop. I was thinking maybe the best way maybe what should be done here is to go a little bit lower. Now we should see the thread here just slightly go slack. Okay, so let me release it a little bit lower. I couldn't, did you guys see, did it look like it went slack? Okay, so that's the appropriate thing to do. So this looks like we nailed it. It looks pretty close, right? This is confirmation here of the theory. Any questions or comments about that? It's a good demo. I think it's a good demo. And you never know what's going to happen when you come up with demos. I got a call from the Exploratorium yesterday. Do you guys know what the Exploratorium is? It's world famous.
Should I know?
Yes, you should. It was the first major hands-on science museum. It's been copied around. People around the world now do this. Before that, you just came and you looked, and you might read something and you just stood there and looked at something static. So it was Oppenheimer. Well, it was. I can't get into the history here, but it was the first one back in the 1960s. So they're doing a display of an experiment. Some students, a thesis, some students and I did here. It's using bubbles to sink a floating body.
Where's it at?
It's in San Francisco. Yeah. Oh, you have to go there. Yeah, you just have to. And be prepared to stay a long time, especially if you have kids. Okay. So the next topic here, this is kind of a short topic. we go through it because it's important for, it plays a role in this course a little bit, but it's really for other physics courses, other subjects. Oscillations, which we unfortunately can't get to in this course. Oscillations like a pendulum like this. It's useful to look at what are called one-dimensional potential energy curves, and I'll explain this. It's especially useful in quantum mechanics, modern physics and quantum mechanics, which, I don't know, Damon wants to take. I don't know if the rest of you are going to take it. But so let's go through this, okay? It's pretty short. Remember here that this is how we define the change in potential energy for a conservative force. It's minus the work done by the force over some interval. That was our definition. And the work done by the force is the force times the distance. We're thinking of these as small now. We're thinking of these deltas as small here. So you can see here that we can solve this for the force. Now this may seem strange to you because you might think, well, the natural thing to do is we have forces, and from that we define the potential energy or the change in potential energy. Well, it's not always true. A lot of times you know the potential energy, but you don't know the force. This can happen in things like particle physics and stuff like that. So the point here is that if we know the force, we can get the change in potential energy. If we know the change in potential energy, we can get the force. And here's what it is. We take the limit as the deltas go to 0. So we just get this in one dimension. The force is minus the derivative of the potential energy with respect to x. So if we know the potential energy, we can get the force. We can go either way now. And this is not at all surprising that it involves differentiation, because remember, to get the potential energy when it's not small, we have to integrate the force. So what's the opposite of integration? Differentiation. So that's what we're seeing here. So this is useful, as we'll see, because the pictorial representation here is not of the force, it's of the potential energy. It's very useful, and you'll be able to see this in a moment. We'll start off with a simple example here, spring. So here's the potential energy in a spring, where x is measured from the relaxed state. X equals 0. The origin corresponds to the spring being unstretched. Okay, or not compressed, either way. So this is the potential energy. The force is supposed to be minus the derivative of that. Is that what we get? Well, if you take minus the derivative of this, you get the force is minus kx. Does that look familiar? That's Hooke's law. So it works. Okay, this is an example of just showing you how that this works. So next, let's consider a single body moving in one dimension and with a conservative force or conservative forces. We know that the kinetic energy plus the potential energy is a constant of motion. That's conservation of mechanical energy, right, that we discussed yesterday. So for a spring here, here's the potential energy. It's a parabola, like we just saw here. So we can graph that, sketch it. The potential 1/2 kx squared. So the total energy is going to be constant. And I know it can't be up here or down here. I know it has to go right through here. Why does it have to go right through the apex of the kinetic energy here?
It has to be conserved. It can't be more.
Right. Because here, at x equals 0, there's no potential energy. The energy is all kinetic. Actually, I think I'm looking at this. Let me back up here. Here's the potential energy. Okay? Here's the way you should look at it. Here's the potential energy. The kinetic energy has to be constant. Okay? And where do I set that? Where do I set the constant? Well, we need to know. We need some kind of initial condition. It could be anywhere here. It could be anywhere. So in this case, we can imagine it this way. Suppose we got a mass on the end of a spring. Suppose we pull the mass over some distance a, and we release it from rest. Okay, so this is capital A. It's being released from rest here. So there's no kinetic energy when x is equal to a, because we're releasing it from rest. The mass is going to move this way. It's going to pick up kinetic energy. It's going to lose potential energy and pick up kinetic energy. And the sum of them have to be a constant. When we get to here, the energy is going to be all kinetic. Here the energy is all potential. So it will, the way to look at this is forget the kinetic energy curve. And that's what we're going to do incidentally anyway, in a while, you'll see. If I started off at rest here, I know that initially my system has this amount of potential energy and there's no kinetic. So I know the line has to go through here. I know the line has to go through there. Once I know this, it's released from rest here, I know that the energy has to look like that. Now I know that the kinetic energy has to start off with 0. Now I know that it's going to peak out there because the energy has to be constant. So what happens here, this is called the amplitude. We call this the amplitude, this quantity A here. The mass is going to go back and forth, oscillating symmetrically about equilibrium. So we have this, we're tying down the spring at one point here, we got a mass here, here it's in equilibrium. The mass is just going to go back and forth like this. And as it goes back and forth, the total energy is constant, but the kinetic and potential energies are continually changing, right? But their sum has to be a constant. I think we've used this terminology before. These are called turning points of the motion because it's turning around. I think have I used that before with you guys? Turning points? Or maybe we haven't. So anyway, where it turns around here, those are called turning points, which is a good, appropriate thing. Okay, now let's just jump, make a big leap here. Let's suppose we're given some potential energy. It looks like this. And you might say, well, this can't happen. Well, you might be surprised, okay? I'll tell you this. This can happen. Without this hump here, if you imagine this curve goes like this and goes like that, that's a famous potential energy. That models the potential energy of 2 atoms in a diatomic molecule or something like that. So you can come up with some weird potential energy curves. Okay, so let's look at this now. Let me look at the notes here first. Now, I want to point something out, and I didn't really point it out in the notes here. This is the potential energy as a function of x, right? The total energy has to be constant, right? It's going to be, and there's different possible values. We can have, the total energy can be up here. It can be sort of in this range. We'll call that E3. It can be here, and it can be, for example, right there. We're going to look at each one of those in turn. But I want to point out here is that I'm not going to try to sketch the kinetic energy on top of this. It's just, it'll just get ugly, okay? But once we know the total energy and we know the potential energy, we can get the kinetic energy, right? The kinetic energy is just going to be the difference. Because the sum of the kinetic and the potential is there. So let's start looking at this here. Let me make sure. Oh. Okay, yeah. Now, the way a lot of people look at this, and I have to admit I'm one of them, is we have this one-dimensional motion. They imagine that this is a wire that's been carefully bent, smoothly bent, in this shape, and you're in a uniform gravitational field, and you have a bead of mass that can slide frictionlessly on the wire. So this gives you a physical picture of what's going on. And the reason it works is, in a gravitational field, uniform gravitational field, I have a bead of mass. What's the potential energy of that bead of mass? It's mg times y, right? Well, that's our wire here is the potential energy, because this is y here in our picture here of the bead of wire on this, a bead of mass on this wire. This is actually y here. So you want to make, if you make the wire conform to the actual potential energy curve here, the gravitational potential energy of the mass on that wire is that curve. So that's a useful picture, but it's dangerous because a bead of wire moving on I don't know why I keep saying a bead of wire. A bead of mass moving on a wire is two-dimensional motion. We're dealing with only one-dimensional motion. So there's a little warning here that you can get in trouble, but it is picturesque. For example, suppose we have our mass has energy E4, and it comes in from here. What's going to happen? We think of if you want to, you can think of a bead of mass on a wire. What's it going to do? It's going to pick up speed, go down here, go up here, go down here. What's going to happen? Once it gets to here, what happens? Yeah, 2 words. Turning point, exactly. So it's going to turn around, and then what's it going to do? It's got to just run off back to infinity. It's going to run off back to infinity. Okay? And if you want to know what the kinetic energy is, you just have to look at the difference here. There's always some kinetic energy, except right at the turning point there, where the kinetic energy momentarily vanishes. Okay, so we call this an unbounded motion. It comes in and goes back out. What about E3? So now, can the mass be over here? No, it doesn't have, it can't be there. It doesn't have enough energy. It'll never be there. So you can imagine, let's say, starting it from here. We can release it from rest here. Because here the energy, at this point, the energy equals the potential energy. There's no kinetic energy. What's it going to do? You can see it, right? That's why people think of this as a bead of mass on a wire, smooth wire. It's going to go like this. It's going to speed up here. It's going to slow down. Can it make it over that bump?
Yes.
Yeah, because it's got, and in fact, the kinetic energy it's going to have is that amount right there on this energy scale here. It makes it over, and then what's it going to do? Turn around there and come right back. It's an oscillator. It's an oscillator. Okay, what about E2? Now what does it do? What? I can't hear.
It won't make it over the hump.
Well, before that we have a problem. Yeah, you're right. First of all, where's the mass? We call this a well, a potential energy well, very common language in quantum mechanics, and modern physics too. We need to specify what well it's going to be in, right? We have 2 possibilities. We could, for example, we could release it from rest here, and it's going to go like this, or we can release it from rest here, it's going to go like that. Okay. How about E1? Well, it's just going to go there, and it can't make it over. It doesn't have energy to make it over. Now, yeah?
And so then you talk about it in terms of being bounded then from E3 below, correct?
These are all called bound states. Yeah, the motion is bounded. It doesn't run off to infinity. There are, situations where things are unbounded. Scattering. When a particle comes in, a body comes in and collides with another body. We're going to talk about this. That's not bounded motion. It just comes in and then they go out like that. But these are oscillatory states that corresponding to the fact that it's bound motion, not running away. So E1 is it's unbounded motion. Here's something interesting. So if I started off here, it can never go there, right? That's actually wrong. If this is a little tiny well here, and this is an electron, it can tunnel through. That's called tunneling. That's a purely quantum mechanical, it's a quantum mechanical effect. And it's actually utilized in what's called a scanning tunneling microscope. We have one downstairs. Have you guys ever heard of a scanning tunneling microscope? It's a way of taking pictures, of getting images of very small objects on the scale of an atom. So it is possible in quantum mechanics, because a particle acts like a wave. Waves can tunnel through a barrier, it turns out. Classical waves can tunnel through a barrier. But particles, we think, well, this is never going to make it through. Well, that's true for our classical mechanics course, but not in quantum mechanics.
Does it lose energy when it does that?
Nope. I mean, it can, but theoretically, there's no problem with that. Yeah, it seems strange, doesn't it? How can it doesn't have the energy to penetrate it. You can't go any farther. But you got to remember something here on the microscopic, level of an atom like that. These particles don't behave classically. They behave like waves. They have particle properties, but they are described by waves. They can interfere with each other. A particle can interfere with itself. Strange stuff. This is why there's a modern physics course that many students take. right? Modern physics is sort of pre-quantum mechanics. Quantum mechanics, you get into the mathematics of all this, but the modern physics is more of a conceptual course. It's quantitative, but it's more conceptual, and it's a very popular course. I think we talked about this maybe, right? Because so many devices now are quantum mechanical. If you want to understand what a lot of your, what's going on with a lot of systems, you need to know some basic modern physics. So we have a course here. I'm teaching it right now. Right? I think I told you that. Okay. Now there's a little bit more here. Suppose I release the ball from rest here. What does it do? It just stays there, right? What if I give it a little tiny kick? What's it going to do? It's just going to oscillate back and forth just a little bit, right? This is called equilibrium when the force vanishes. Remember, the force is the slope, and the slope is 0 here. That's why we did that. That's one of the reasons, main reason actually. So there's no force. No force, we have a word for that, equilibrium. The particle's in equilibrium. And if we disturb it, it doesn't run away. Similarly here. But what about here? Is that equilibrium? Yes, it is equilibrium. But what's different from this? What's different about this compared to these two cases? I don't know if I heard it. What?
It's unstable?
Yeah, we have a word for it. It's unstable. The slightest little, you can rest this theoretically, with no fluctuation. If there are no vibrations, you can rest the mass here. We can think of this as the bead of wire, and it'll stay there, right? Theoretically, I can rest this pin on here, right? If I do it just right, and it'll stay there. But it's not going to stay there. Why doesn't it stay there? Well, there are little fluctuations. A slight fluctuation here, the slightest fluctuation, it's gone. We call that unstable equilibrium. Right. We don't need to worry about neutral equilibrium. You can look at this if you're interested. It's kind of boring. So when we talk about systems being in equilibrium, we have to distinguish between stable equilibrium and unstable. So here's a standard example. This is a pendulum, okay? Equilibrium. Is it stable or unstable? Stable. It's obviously stable. What about this? This is still a pendulum, right? Is this stable or unstable? It's unstable. It's called an inverted pendulum. It's unstable. Clearly unstable. One of the things that's interesting about this is that if you shake the support here, you can actually stabilize it. That's called parametric stabilization. I'm doing some research on that right now. That's why I mentioned it, I guess. So just because things are unstable doesn't mean that you want to stay away from it. Okay? So the research we're doing has to do with, for example, submarines. A submarine that's neutrally buoyant, right? Is that stable or unstable? Did we talk about this before?
Yeah.
Do we have any submariners in here? Everyone's looking at Aaron? No, Andrew and Aaron look at each other. Oh, all right, Luke. So do you guys, you're supposed to know this. I wrote it into the thesis. I wrote it into a video. We're working on this. But all submarine officers are aware of this. Yeah, you could have a submarine that's neutrally buoyant, but slight fluctuation, it'll just boom, rise to the top, or go to the bottom. You have to keep monitoring it. It's like an inverted pendulum. You have to keep doing something, like this. I know this doesn't look like a submarine, but to a physicist, it is. Okay. So you guys didn't know that? Yeah. All. I can't. I got to stop, or we're not going to get through. Sorry. I should never have begun. Okay, so that's it for one dimension. Let's just to introduce it to you. We'll do some simple probes at it. But you can see it's nice and picturesque, right? And you can take something that's, one of the advantages of this is, this is complicated here. But we can make definite statements about the motion of a mass in here, just based on this picture. That's why this is so popular, these one-dimensional potential energy curves. Okay, the next topic has to do with what I think Damon brought it up yesterday. How do we handle friction? There's no potential, or drag. How do we handle non-conservative forces when it comes to energy conservation? Well, they don't have a potential energy, as we discussed yesterday. So here's how we handle it. So the prime example for us is going to be friction. That's our standard case. But this holds true. The basic idea, the basic theory here, you can apply it to any non-conservative force. So let's actually proceed along those lines. Let's make it very general here. A force is either conservative or non-conservative. It's got to be one or the other, and only one. So that means that the total net force, I can lump all the conservative forces together. There could be any number, and I'm going to call that F sub c. So this is the net conservative force. And what's left over, the non-conservative forces, this will be the net non-conservative force. All right? So we do this because we know how to handle this. We know that, oh, sorry, I'm getting a little ahead here. We split the forces up like this into these two groups. What's the work done by the net force? Well, I dot this with dr and then integrate it, right? That gives me, on the left-hand side, it's going to give me the work done by the net force. When I dot this with r, I can distribute the dot product over these two terms, and in the integration, I distribute over two terms. So this has to be true. The fact that the forces are additive here means that the works have to be additive. And to see that, all you have to do is take this equation and dot each side with dr and integrate. You're going to end up with this. Because this is linear, because these are just superposed here. The works are going to be superposed. Now, we know how to handle this. Remember the work kinetic energy theorem. Oh, sorry, I keep getting ahead of myself. I'm sorry. This is true. Regardless, we never talked about conservative and non-conservative forces when we did this. So this is absolutely true in mechanics, and in this class. This is true, okay, that the change in kinetic energy is the work done by the net force. And you can look back, and we derived it in general from Newton's second law. So what that means is I can set this equal to the change in kinetic energy. Right? That's all I've done here. I've used this in here. Now, the next step is what we did yesterday, I think. Because these are conservative forces, a potential energy function is going to exist. So this is how we came up with conservation of mechanical energy. We set this equal to minus the change in potential energy, and then we brought it over to this side of the equation. Remember, that was the big step, right? And then we can see that we have the change in total mechanical energy here. So that's what we do here. It's just that we've got this extra term. We can't do anything with this. Okay, this is just is along for the ride. So in the end, here's what we get. We replace this with minus the change in potential energy, the conservative forces. Bring it over here. That's going to be the change in total energy. That's going to equal the work done by non-conservative forces. So here's what we have. Here's the basic theory. The change in mechanical energy, which is the kinetic plus the potential energy, is identical to the work done by the net non-conservative force. So before, this was zero for us because we assumed only conservative forces. Now it's generalized here. So that's the basic idea. This allows us to do some calculations, okay, and we're going to do one shortly. But first of all, let me make sure you realize what's going on here. So in words, the change in mechanical energy of the system equals the work done by non-conservative forces. And before we had this, because we had only conservative forces before. So I know this is disappointing. We really didn't do anything here. We just, we use the work kinetic energy theorem, and we just can't analyze it any further. We just have to leave this here. So let's see how this works in practice. Let's do an example. Now the typical case with, we're going to do a friction example. The typical case with friction is where the surface is not moving. So if I have an object moving on a surface here, the work done by friction is what? Is it positive or negative or zero? I got something moving this way. Okay. Something moving this way. Where's the kinetic frictional force? Points this way. The displacement's this way. The work done by friction is negative, right? So what's going to happen here is, what happens to our mechanical energy? It goes down. And I'm sure you all suspected this anyway, and we'll talk more about that in the final section here. But so that's the typical case. Why do I have to say typical? Well, this surface could be moving. In fact, there's a quiz problem. So has everyone turned in the quiz? I think there might be one. Is everyone? Okay. Now I do drop the lowest. You know, you're free not to turn in one because I dropped the lowest one, right? Okay. I just wanted to make sure because I counted this morning and I was way off. But since then, some people have turned it right. A couple of. Okay. So there's a problem on there about involving friction where there's a block on top of another block. Yeah, now that's static friction. But in this case, you can imagine that this table is moving, right? And if I abruptly start moving this table, this thing's just going to sit here. If I break the static friction. And then what's going to happen? It's going to actually, where's the frictional force point on it? This way. It's going to accelerate it. Friction accelerates it in this case. That's an unusual case for our class, but I just have to mention, for completeness, I have to mention it. The work done by friction is not always negative. Here, the friction, if I move the table, I'm moving like this and causing this to exerting a force on this way, on this mass here. I'm going to accelerate it. The frictional force the work done by friction is positive in that case, but that is unusual, especially for this class. Okay, so we're going to do an example now. Anybody have any questions before we get into this? This is sort of we've done something similar to this before, but now we're going to do it from the point of view of this. And you'll notice that we have two forces here that are important. There's a normal force, there's a gravitational force, but what's important is the force of the spring and the force due to friction. So we have a rough surface here. The entire surface is rough. It's all rough everywhere here. The roughness doesn't start here, okay? The whole surface is rough. So this is a little bit more realistic than perhaps normal. And the situation is this. We compress the spring with the mass on the end of it. We compress this down 50 centimeters. And then we release it from rest. And I was actually worried about this an hour ago. The static friction is not, you'd have to have huge static friction to keep this thing from moving, okay? The static friction is going to be broken. But I have to admit, if you had an extremely large static friction coefficient, you know that if I release this from rest, if it's big enough, this thing's not going to move. You know that. We've been through, things like, we've been through that subject. Okay, so what we're going to do here is we're going to split this up into two problems. We're going to ask, what's the velocity of the mass right when the spring is unstretched, relaxed here? So that would be the initial velocity for the rest of the motion here. We're going to find the velocity here. This is corresponding to where the spring is unstretched. And then we're going to find out how far it goes. That's the problem here. So the first part of the motion, we're going to call this the initial state and this the final state. We're free to do that. I've tried to emphasize this in the past. If I care about the velocity here that the spring launches this thing at, I don't care about the rest of this. I'm going to call this my final state. I can do that, okay? Later, we'll call this the initial state and that the final state. We're free to do that. So what's the initial energy? It's all in the spring, right? 1/2 kx squared. So I'm going to go ahead and calculate that. I got 50 joules of initial energy. Now, taking this to be our final point, right? That's an F there. What's the final mechanical energy? We really should say mechanical here. I'll talk more about that in the final section. What's the final mechanical energy here? Well, there's no energy in the spring. It's all kinetic. And that's what we want to find is V, okay? So our theory tells us that we have to find the change in mechanical energy. This minus that has to be the work done by friction. What's the work? I'm going to edit this and improve this. I don't like this absolute value thing. What's important here is this distance. The work done by friction is opposite the motion, so the work is done by friction is going to be negative here. And it's just going to be the frictional force, which is the coefficient of friction times the normal force. The normal force is mg, times the distance. So there's no doubt about it, this is the work, in our case, the work done by the non-conservative forces here. There's just kinetic friction is equal to this. And we can calculate that, and it's minus 5.9 joules. All right, so here's the idea. Well, let me go through the math. And then the change in mechanical energy is the finest minus the initial, and it has to be this is our theory. It has to be the work done by non-conservative forces, friction here. So here's the change. The final energy minus the initial energy has to be minus 5.9 joules. I've got one equation and one unknown. I can solve for the velocity. Now, we went through the math here, but you want to make sure you see the physics here. What's happening to the mechanical energy here? As this mass moves along here, what's happening to the total mechanical energy? The energy in the spring plus the kinetic energy of the mass. Is it constant? No, the frictional force is impeding the motion. As we'll see in a moment, we're losing energy to friction due to heating of the surface. And we'll talk about that. That'll be the final thing we talk about. But that's the idea here. That's how you want to think about this. We went through the math here. I just wanted to go through the math just so you can see how it works. But the way we conceptualize this is we're losing mechanical energy. The energy in the spring is not going to all be given to the energy of that mass when it's launched. We lose some to friction. Right? And it's 5.9 joules is how much we lose. If we don't lose that 5.9 joules, you can easily calculate, you get 7.1 meters per second. That's an easy calculation, right? For smooth surface, you just set the potential energy in the spring equal to the final kinetic energy, you're going to get 7.1 meters per second. Okay, so that's the first part of the problem. Anybody have any questions about that? Okay, now the second part of the problem is, let me go back up here. Now we're going to start from here and end here, okay? So now, well, we know the initial velocity. We've solved the problem we've essentially solved this problem before. Given a block on a surface with an initial velocity, it's only going to go a certain finite distance. Remember, that's the first problem we did after we came up with kinetic friction. We solved that. But we want to do it here from our theory point of view. The change in mechanical energy is we're going to do it differently here, right? So we can do this based on Newton's second law. We did that. You can look back. But we want to exhibit our energy theory here. Okay, so the initial energy is all kinetic, and it's 44.1 joules. We calculated that, I guess, before, or we can calculate it. This is mechanical energy. What's the final mechanical energy? 0. There's no kinetic, no potential. There's been no change in potential energy. So the final energy is 0. The work done by the non-conservative force is just the frictional force, the kinetic frictional force, times the distance. And we've got to have a minus sign because they're opposing. The motion is this way and the kinetic frictional force is that way. So it's going to be this. Now I'm going to take the opportunity here to do something that engineers love to do, but it's really dangerous. In fact, most physicists don't do it. Look what I've got here. I've got this. I'm going to set this equal to the change in mechanical energy and solve the problem, right? But I don't know D, that's what we're after. But I know these numbers. So it's natural to punch these in and come up with a number here. But there's a big problem here. Going from here to here, you'll notice I've used SI units, right? This is only true when D is in SI units, in meters. This is always true. You can use any units you want to here. As long as you stick, you're correct in manipulating whatever you use, you can use any units. This is a general formula. Once I go right here, it starts right here. It's not here, it actually starts here. This is only true if D is in meters. So you need to state that. And engineers, because they typically do a lot of numerical calculations like this, it's a common thing for them to do is to write this. And then they won't write this. Have you ever noticed, have you ever seen this before? Have you ever looked up some formula or something for some complicated thing that maybe is described empirically, and they give you some formula? You guys ever done this? You've got to be really careful about this. At this point right here, this is only true if D is in meters, because everything else is in SI units, so D has to. If you plug in centimeters, you're going to be off by a factor of 100. Okay, so you want to be very careful about this. Anyway, so we use our theory here. The change in mechanical energy is the work done by non-conservative forces, which in this case is the kinetic frictional force. And it all works out, D is positive. The signs cancel here and we get a number. Okay, so we'll do an example like this in the homework tomorrow. I guess it's going to be tomorrow. Okay, anybody have any questions? So that's how we handle non-conservative forces. We're relying on the work kinetic energy theorem. We really can't simplify it. Well, we can simplify it, but it's debatable whether it's useful or not. Incidentally, this mistake in the early or mid 2000s, there was a spacecraft, I think it was a Mars rover, that crashed on the surface of Mars. I don't know if you guys remember this. Do you know, all physics teachers know what the problem was? They were using formulas where a quantity had to be in certain units to be correct, and it was in probably a computer program or something, and the code, it was wrong. It's like somebody plugged in centimeters instead of meters there. So this is a famous case where you want to be really careful about this. It's people do it because it's convenient, but often there's a price for convenience. All right, so there's one more thing we need to talk about here, and that's look outside mechanics and think more generally here about conservation of energy. So what we've actually been doing is the conservation of mechanical energy. Okay, and I was careful, sometimes I'm careful when I said this. For example, if you look back here, right when we first hit it, the total mechanical energy is constant, all right? And our work with friction brings up another fact, and we've talked about this. When friction occurs, there's going to be some heating in the surface. And what that is the molecules in their atoms are jiggling around. They pick up kinetic energy. That's what heat is. It's microscopic kinetic energy. So we want to talk about how we think about that. So where is it? All right. Let's go back to, I'm going to change this. Let's go back to this. Can everybody see this? all right? And initially, this has some kinetic energy, some mechanical energy. Finally, what's the mechanical energy? It's 0. So, it's natural to ask, what's happened to that energy? The answer is, that I just told you, is that it's gone into heat. A little bit it's disturbed the air. It's actually increased the temperature of the air a little due to drag. But mainly here it's going to be the frictions. These two surfaces are going to heat up a little bit. And that accounts for the energy loss. In fact, centuries of research, I like the way this is stated here. Centuries of research have shown one fact again and again, that if we include the energy in the heat here, heat is energy. If we include that, the energy is conserved. The total energy is constant. So that's the conservation of energy. And it applies not just to mechanics and thermodynamics, but anything else you can imagine. If you have an isolated system, okay, no influence from the outside, the total energy has to be constant. So no one really questions that anymore. And as I think I might have said before, if you do see what appears to be a violation, you look around for some other source of energy or some mistake, like in the video that Gene and I did. Have you guys, I hope you guys, it's only 3 minutes long, I think. Yeah, so that's an example of, it's not that we were missing a source of energy there. These one ramp, only three of the, there was one ramp that wasn't projecting the ball horizontally. It was at an angle. So there was a mistake there. All right, that accounts for the so-called violation of kinetic energy there. But as far as anyone knows, any serious person knows, you can't violate this. This is an absolute limit. That energy and total energy in an isolated system is constant. So what that means is we can look at this simple system here, where I give this eraser some initial velocity and it's moving along here. Its mechanical energy, its kinetic energy is decreasing, but an equal amount of energy is going into heating this surface. We can look at it looking from a total energy point of view. We can say that the change in the total energy is the change in kinetic energy, the kinetic energy of this, okay? Plus the change in potential energy happens to be 0 here, plus the change in thermal energy. And because of its heating up, that's got energy. So in the end, we start off with some kinetic energy. All that energy is going to go into, that precisely amount is going to go up into heating the surfaces here. So this actually offers a different way of solving problems than from this approach. And I didn't check. So we just solved the problem using this, right? I can't remember how our textbook handles this, but I've thought about this. I've been through this a lot. This is how we want to solve problems. There is a slight alternative. We can essentially bring this over to this side of the equation if we include thermal, in this case, thermal losses. But I don't think it's worth it for this course. It's not worth it to do that. So I want to encourage you not to do that, and that's what in the homework, that's what we'll do. So this actually, we can actually solve problems like this, but I think it's actually more general, and it's calculationally easier to not use this in this course, to use what we just did. Okay?
So are we just making in this course just 0 for simplistic purposes? Is that
what's 0? This?
Yes.
No, we do friction. When we do friction, there's changes in it's heating up. So all I'm saying right now is when you have friction, you could use this to solve problems. And it's going to be essentially the same. But it's better not to use this. This is just a calculational thing. It's better to use this. They're equivalent. That's all I'm saying here. And we'll do something. So we're going to do problems from this example. And I can't remember what the textbook. But you need to get the concept here. This is the concept. The total energy is conserved of an isolated system. But you have to include all forms of energy that are playing a role in the transfer of energy. Do we worry about gravitational potential energy here? No, there's no change in gravitational, so we don't worry about it. We don't need to include it in here because it's not changing. But when you've got friction like this, or like drag, where things are heating up, that's a sink of energy, or it's a type of energy, and you need to include it. Okay, so just one final remark here. I keep talking about an isolated system, right? And you say, well, what about systems that aren't isolated? Well, let's look at that. It's simple. This is simple, as you'll see. So here's some system, here's A, some system B. Let's suppose that A causes the energy of B to go up by a certain amount. Let's say it goes up. It could go up or down, doesn't matter. But let's say that A causes B, the energy of B, to change by an amount, delta EB. Now, okay, that's fine. If I'm free, however, to view the total system here. So that's what this dashed line represents. Now we have an isolated system. And I'm going to write that here. I need to edit that in here. So now what has to be true for an isolated system? The energy has to be constant. Right. So if the energy's gone up by a certain amount here, what has to have happened here? It's gone down by the same amount. That's energy conservation. So we can use, we're actually not restricting ourselves, to, we can always come up with an isolated system. Now, but here's something that might surprise you. Suppose, here's our system. Here's like A and here's B, including the Earth. This is system A. A does work on B, lifts this mass up and puts it on the table. So there's an mgh, is the amount of work done by system A here. Okay, how much, so this system has increased by an amount of energy mgh. What is the energy of the person decreased by? Has to be mgh. That person has to have lost a total energy of mgh. It may be hard to measure, but if you go in there and look at all the processes that are involved, and the heating and muscles and all that, the energy of this person has to have gone down. Okay? What if the person now takes the mass and puts it back down here? Now what's happening? The total energy of this system is going down, so what's the energy, what's happened to the person? The energy has to go up. So here, taking this mass and going back down here, now energy is going from the system of the mass and the Earth back to the person. The energy will go up. Now, you've all probably done some, I know that seems strange, right? If you're doing some kind of weightlifting or something like that, you'd say, oh, you're doing work here. You're doing positive work. And you feel like you're doing work here, but you're not. It's actually negative work. This system is doing work on you. It's putting energy into you. And if you did, it's probably impossible, but if you could do very careful measurements, you would find that the energy of the person has gone up by mgh. It has to be. It has to be.
Could it transfers to, you're including the Earth and whatnot, transfer to another part of the system besides the Earth?
See, I've been careful about this here. System A is just the person. System B, because we want to think of the gravitational potential energy, it includes the table, the mass, and the Earth. That's system B.
Okay.
And I think the statement is precise here and it's correct, yeah?
Energy in the form under what, though?
Oh. You're dealing with biology here. I don't touch that. Right? There's going to be, there's all kinds of, there's, elastic, there's spring constants in your muscles, there's heating, there's going to be heating. There can be chemical changes. You eat, energy is conserved, right? The reason you can do things is you're converting energy from the food you eat, right? So there can be these chemical processes and dealing with, I don't know. I'm not going to touch that.